For this system here, we want to determine the tension developed in each of the cables for equilibrium of this 300-pound crate. So in statics, this is a problem that falls under the category of particle equilibrium. In particular, this is a three-dimensional problem. I don't even want to call this like a 3D particle equilibrium problem. I don't like putting that in the title, but I do. Because this is just a particle equilibrium problem. It just happens to be in 3 dimensions. The physical principles are exactly the same as what we did in 2D. It's just now we're in 3 dimensions, so we have to work with 3D vectors. So the math is a little bit harder, but the statics, engineering mechanics principles are exactly the same. Why is this a particle equilibrium problem? Well, the first hint is that we see this system of cables. And if you end up drawing a free body diagram where all of the forces acting on the component that you're doing the free body diagram for are from cables or springs or slings, chains, then it's going to be a particle equilibrium problem, meaning that all of the forces, the line of action of all of the forces that are acting on your free body diagram meet at a point. And for the equilibrium case, where the sum of the forces are equal to 0, that point doesn't necessarily have to be the center of mass of the component. If the sum of the forces aren't equal to 0, it's different, and we'll get to that in dynamics. So that point where all the forces meet, you can just draw your free body diagram as a point and put all of the forces acting at that point. Or you can draw out the component and then put the point where all the forces meet. If you want to do that for visual, like as a visual aid, just to see the component, you can do that. Okay. So let's get to the problem here. So for this type of problem where you've got it's a system of cables, which you can typically find is 2 parts of the system. One part is like the working part. So this is holding the crate. The other part is associated with like the grounds, like where the structural part, like attached to, see, these cables are attached to ground or to the wall. And then there's a piece that's connecting these 2 parts. That's the piece that you're going to do particle equilibrium on. So the line of action of, so if this is going to be our point that we're going to do our free body diagram, because all the line of action of all of the forces from the cables are meeting at this point. All right, so that's this point. Next, the next thing we see is that the origin, the coordinate system that they provide, the origin is not at that point. We're going to go ahead and put the origin of our coordinate system at that point. I've mentioned before that for particle equilibrium problems, it doesn't matter where you put the origin of your coordinate system. But for other types of problems, for non-particle equilibrium, you can't just move the coordinate system like that. You can, but then you'll have to make some other changes to your forces. And we'll talk about that in future videos. But we could leave the coordinate system here and get the same results. And so what we would do is we would say, this is our coordinate system, and we would put, okay, our point is here, and it's 6 feet, and then we would draw our forces from here. You see, like this would be AD, AB, AC, we like that. And so, I mean, we could have done that, but I think this is a little easier. Okay, so we've got our point, we've got our coordinate system. Now let's apply the forces to this point. We've got a downward force from the crate. This is 300 pounds. All right. We've got a force. So like imagine we're coming from here now. So we've got a force that's going from A to C, kind of in the positive X direction, something like that. Okay, and then we've got a force going from A to B, a little bit further down, kind of like that. And then we've got a force going from A to D that has no component in the X. It's a little steeper than those first two forces. Something like that. And so this is, we'll call it T. TAD. TAB. TAC. Okay, and typically a proper free body diagram has dimensions on it as well, but we're just going to go ahead and reference these dimensions. Okay, so in 2D, you can just typically just go straight to doing the some of your forces. But because 3D is a little more involved, we need to define these vectors a little more clearly. So the weight of the crate, we'll bold this because this is a vector. The vector W from the weight of the crate. This is an easy one. This is just minus 300 k hat. All right. What about vector TAC? Okay. This is, so the magnitude of TAC. Okay. What are the components of we need to get a unit vector going from A to C because we're going to multiply the tension in cable AC by the unit vector in this direction. So going from A to C. Oh, and I forgot to mention, we know the sense of these vectors. It technically wouldn't matter. We could have just if we would have put, like, okay, we know these cables can't support compression, so we know that these forces are going to have to be pulling on this point in this direction. But we technically could have put the wrong direction for all three of these, and then we would get negative answers, and so we would know that the sense is the opposite direction. The only thing we have to get exactly right is this 300 pounds going down. We can't guess this as going up because we're applying that force to the system. This is a known force. All right, so again, this point, the vector that's pulling at point A from cable AC is going from, the direction is from A to C. So A to C, we go 2 in the I minus 6 in the J and plus 3 in the K. All right, and if you work out the magnitude of this, so 2 squared plus 6 squared plus 3 squared, you get 49. Square root of 49 is 7. So there's our unit vector. Now let's just simplify this. We've got 2/7 I minus 6/7 J plus 3/7 K. Okay. Now let's do force vector AB in cable AB. So the magnitude of the tension in AB, and now we just need to write out a unit vector going in the direction of AB. So that is minus 3I minus 6J. Again, our origin is here. We moved our origin on our free body diagram to this point. Okay, plus 2K. All right, and then we're going to have it's going to be the magnitude of this vector is 7 as well. See, we have a 2, it's the same. We have a 2, a 6, and a 3 for both of these. So let's simplify this. Okay, so now let's write out the force vector in cable AD. So the tension in AD, and then we're 0 in the I, plus 3 in the J, plus 4 in the K. Okay, 3 squared is 9, 4 squared is 16, 25 squared 25 is 5. All right, so all right, so now that our force vectors are clearly defined, now we can sum our forces. So let's sum the forces by the x, y, and z, and we know that all are going to be equal to 0. All of these are going to be equal to 0 because this point is not moving. Okay, so we've got 2/7 TAC minus 3/7 TAB is equal to 0. Okay, so this is what? We have 2/7 TAC is equal to 3/7 TAB. So TAC is equal to 3/7 times 7/2 TAB. So TAC is equal to 3/2 TAB. All right. Now let's sum the forces in the y. This is going to be equal to 0. So we've got minus 6/7 TAC minus 6/7 TAB (3/5) TAD is equal to 0. So let's go ahead and substitute this TAC here. So we've got minus 6/7 Okay. So we have minus okay. So we can combine these. So minus 9 minus 6. So you get minus 15/7 TAB. And so now let's go ahead and bring, so like this is minus 15/7. So then we know that this is we can bring over we can bring the minus 15/7 over and get this equality. So what we have is TAB is equal to, and then we could, so 3/5 times 7/15 is 7/25. So Okay, so now let's sum the forces in the Z. So we've got minus 300 plus 3/7 TAC plus 2/7 TAB four-fifths TAD is equal to 0. Okay, so we moved our equation here, and this is what we solved for already. So what we can do is, once we wrote out once we summed the forces in the x, y, and z, we ended up with 3 equations and 3 unknowns. So right now we're just solving a system of 3 equations and 3 unknowns. So let's plug in for TAC this, and then for TAD we'll plug in 25/7 TAB, and then we can solve for TAB. So we've got minus 300 plus 3/7. So TAC is okay plus all right, now TAD is 25/7 TAB. Okay, so we've got I'll bring that 300 over. So okay, so we've got this is equal to 300. All right, so now we just need to combine this. Let's turn these into fractions with 14 in the denominator. All right, so 9 plus 4 is 13. 40 plus 13 is 53. Okay, so TAB all right, so we've got TAB is equal to 79.2, and this is pounds. All right. Okay, so now let's get TAC using this. So TAC is equal to 3/2 times TAB. TAC is equal to 79.2 times, so 118.9. Okay, now we just need TAD, and let's use this equation. So TAD is 25 over 7 times TAB. Okay, so $282.9. And that's your answers.